Good morning. Welcome to Specialist Math Student Review Program provided by Texas Instruments Australia. My name is Bozenna and I teach at Wesley College, and today we'll have James Moss as the facilitator from Suzanne Corey High School. So what we'll look at today, polar form, which is also called modulus argument form, Euler's form displayed on the CAS calculator. We look at regions in a complex plane and DeMoivre theorem and end roots of a complex number. So, Cartesian rectangular form is z is x plus yi, where x and y are real numbers. The calculator calls it rectangular. Used in specialist maths is r is theta. However, the calculator will display it slightly differently. It will display it as rei theta, where r is the modulus of z, and theta is the argument of z, with the principal argument being between minus pi and pi. So we'll illustrate with some examples how the polar form is on CAS. When do we use polar form? When we raise to high powers using the Moivre theorem, it will be mainly in exam 1 because for CAS it doesn't really matter. It can handle high powers. When we find nth roots of a complex number and when plotting race regions in Argand diagram. Here is the Moivre theorem. If we raise the number to the power n, we raise the modulus to the power n and multiply the argument times n. So let's start with some questions. The first question is a multiple choice question. Root 6 on 2 times 1 plus y expressed in polar form as one of those. So this is the calculator screen here. Let's enter our complex number, square root 6 over 2, and that is times bracket 1 plus, we need to use I from here, and we close the bracket. What we need to do now, we need to convert it into the polar form. So it's number and complex number tool, and it is convert to polar and enter. So the calculator displays it in this form. That's the modulus, square root 3, and the argument is pi on 4. The calculator always displays the principal argument, so we can see that the correct answer is option E here. Second question, express root 2 minus 5 pi on 6 in Cartesian form. So if we start with polar form, we need to, again in the calculator screen, enter this as square root 2, and then we need to use E because we need to enter it, as I said, in Euler's form, and we can use the fraction tool, 5 pi over 6, and remember we need to add I here in the power. And if I press enter, the calculator automatically converts it to Cartesian form. Why is it so? Because in our settings, document settings, if we are automatically in a particular form, that's what it will do. So that is the polar form, the Cartesian form of this number expressed in polar form. Question 3 is asking for the principal argument. So what we can do, we can here just go again to, in our calculator, we go to menu, number, complex number tools, and we wish to find polar angle. It just says angle, and now we'll enter the complex number, which is -3 square root 2, move it, take away, and we enter I, multiply times square root 6, and below the line we have 2 plus 2i. And if we enter, we get the principal argument as 11 pi on 12. So if that's the multiple choice question, our answer is 11 pi on 2. Now, what you can do with the calculator, you could enter the argument which results with some other calculations, not in the principal form, as I did here, minus 15 pi on 4, and the calculator will change it to the principal argument, pi on 4. Another example, 7 pi on 6 goes over, which is not the principal argument. The calculator will display it as the principal argument. So there are just some hints how you can use your calculator efficiently. This is more like extended answer question. Z is root 3 minus I. So we wish to express that in polar form. We have to show that Z to the power 6 is real. And then we wish to find a positive integer n such that Z to n is purely imaginary. So what we'll do, we'll define our Z. So we can say let Z be equal square root 3 and take away I. So calculator remembers that that's what Z is. Now we'll convert it using complex number tool. Convert to polar, enter. So this number in polar form is 2/5 minus pi on 6. We know it is the fourth quadrant, so the argument is negative. Now I can now raise Z to the power of 6, and of course the calculator will show me that it is real. If it is the exam question, show that you will need to take this number, raise it to the power 6, 2 to 6, multiply the argument times 6, which will result in 2/6 minus pi, and 2/6 minus pi is minus 64. So that will be enough to show that question. Now, what we have in part C is find a positive integer n such that Z to n is purely imaginary. So I do it in steps. I will find Z to the power n first. So, of course, modulus raised to the power argument multiply. And now I will go menu, number, complex number tools, and I will find the real part of this number. Enter. So that's my real part. I want the real part to be 0 because I want my number to only have an imaginary part. So what we'll do, we'll go menu, algebra, solve, and I take my equation, and I will say that this is equal to 0, comma, n. So the calculator gives me the general answer because it's solving the trigonometric equation. Now, if I make n1 0, I will get 3 times minus 1, which is minus 3, which is not a positive integer. If n is 1, 2 times 1 is 2, minus 1 is 1 times 3 should work. So I can, of course, check Z to the power 3, enter, and yes, it's purely imaginary. If you want to convince yourself, you can check other powers and you will see that it's not what we want, squared, and so on. So the smallest positive integer here will be 3. So what we did again, we changed to the polar form, we raised to the power 6, then we raised to the power n, found the real part, solved for 0, and then needed to deduce our number from solutions. Next question is, which complex number lies in the region such that modulus z minus 1 is between 2 and 3? If you did enough questions, you would probably realize that this is between two circles. So what we'll do, we'll again assign z as x plus y times I. I need to do it in each new problem because I'm using a new problem for each question. So now I can find modulus z minus 1, and I say I want that to be less than 3. And then I square both sides. So, oh, sorry, I did it wrong. Go back, not in modulus, try again. Here is less than 3. And then I square both sides. So that's one of the regions. If I do the same, of course, with z minus 1, but this time we had this on here, so I will have 2 is less than this, and I square both sides again, so I get my second region. Now, to see which of those lies in between those two, I will define the relation. Let's call it relation 1 in x and y. And I will say my relation is such that it is in between 4 and 9. So now the calculator remembers that the relation in x and y. This relation, of course, will be sitting there. And now if I put 1 comma square root 3, it says false. So this number does not lie in my relation. Try another one, 1 comma 3, false again. Let's try option C, 2 comma 1. No, not good. Let's try option D, 3 comma negative 1 says true. So therefore, point 3 minus I is the point which lies in this particular region. Next example, the complex number z satisfies modulus z minus 1 is 1. What is the greatest distance that z can be from the point I on the Argand diagram? And we have those 5 options. So again, I will start with saying my z is x plus y times I. And I will find what the region is by saying modulus z minus 1 is equal to 1. And I square both sides. And now I can do menu algebra, complete the square to see that it is the circle with center at 1, 0, and radius 1. To draw it, I don't need to see the circle, but it might be useful for other options. Now I can take this, and you press Ctrl-C, and then we go to the graph, and we change menu to relation and Control V. So we have the circle drawn here. Just move it. We can make it a bit bigger, zoom in somewhere here. I had the grid showing, I might hide grid. So now that's our circle, and now in the question we had point I. So what I can do, I can use menu, geometry, points, lines, and I will put point on the axis. If you go Control menu on your calculator, you can get coordinates and equations. If you get here, I want this point to be 1. So I have this point and the region. So what is the greatest distance? Clearly, it will be this line through the point, through the center to this point. I could draw a segment just to illustrate this. If I go from here to there. Now, if that's 1 and that's 1, this length is square root 2. You could also check the length using measurement and length, but it will only give you the decimal value here. Square root 2 plus 1, if we extend this line, gives us the option D is the answer here. So you can make little constructions like that to visualize the problem and answer questions. Next example here is in an Argand diagram, the points that represent the complex numbers z minus z conjugate, z to minus 1, and minus conjugate of z to minus 1 will always lie at the vertices of either square, rectangle, parallelogram, rhombus, or trapezium. And those questions do appear on the recent exams in general form. So again, I will tell my calculator it's x plus y times I. So that's my z. The next thing I want minus conjugate of z. You might remember that conjugate of z is just CONJ. So that's my x plus yi minus x plus yi. Then I will find z to the power negative 1, which is this funny looking expression. And then we have negative conjugate of z to the power negative 1. So now if we look at those points, they have the same y values, opposite x values. Same here, the same y values, opposite x values, which I have drawn here. So y values the same, x opposite, and here we have negative y values, which are the same, x values opposite. So clearly those two lines are parallel. So we are looking at a trapezium. So the answer here will be option E. Find a point of intersection between the circle and the straight line, and then the circle and the ray. Remember, in the exam, you need to give exact values. So drawing regions won't really be very good. Will not get exact value. We'll use a different function of the calculator now. If we go to menu algebra, you can see we have zeros, okay? So I will use zeros, but I have two different equations. Therefore, if you press the template, you need to use this option here. That allows us to now enter both equations. So if I enter z plus 1, remember in zeros, I have to change this equation to everything to the left-hand side. And then my second equation is the perpendicular bisector, which is z minus 1 equals, and I have modulus z plus 1 minus 2i and actually I didn't say z equals, so what I will need to do here first is I copy this, because it will not work unless I again say my z is equal to. So I need to start with z equals to, because that's a different problem. Y times I, and then I can enter my equation here, and comma x, comma y, and something didn't work. Okay, try again. Zeros, menu, I didn't copy everything. Algebra, zeros. So I have to start over, sorry. Okay. Delete. So, menu, algebra, zeros, and I need to enter two equations. So I have my first equation as modulus z plus 1, and I need to go minus 2. My second equation is modulus z minus 1, and I need to put negative, because as I said, it has to be on the left-hand side, modulus z plus 1 minus 2i, and now I can say comma x, comma y. Hopefully we get the answer. So the answer is displayed as a matrix. So the first point of intersection is root 2 minus 1 root 2. The second point is minus root 2 minus 1 and minus root 2. So these are the exact values. If I want the same circle but the ray, so I can do the same thing, but instead of having the perpendicular bisector, I would need to change this. Doesn't display it very well, but I need to delete here and put a ray, which, as you remember, is angle of z, and it has to be on the left-hand side, so minus 3 pi on 4, and enter, and that gives me the exact value of the point of intersection when the circle is cut by the ray. I have done Cartesian equations of those and drawn it here. So that's our circle, that's the perpendicular bisector and ray. If you are to find the point of intersection as decimal values, you would need to use menu, geometry, and intersection points for relation. Analyze graph does not work for relations. It only works for functions. The last thing we'll look at today are the nth roots of the complex number. We already looked how to find zeros, and I made this file here to show the geometrical interpretation of the roots in the Argand diagram. So if I'm finding cube roots of 1, I can see I have 3 roots. The coefficients are real, 1 real root and 2 occurring in conjugate pairs. But if I change this to I still have 3 roots, but they are not occurring in conjugate pairs because my coefficients are not real. If I change it to fourth root, I have 4 of them with I not conjugate pairs. If I change to 1, they will occur in conjugate pairs. If I have, let's say, power 6, again, I will have 6. And if that's I, they will be looking different. So as you probably learned, if we look at the roots of the complex number, the roots will lie always on that circle with the radius here. Radius will be the 5th root of 32. Because this equation is all real, then we'll have the complex roots occurring in conjugate pairs. If you are to draw it in the paper, you can change radian degrees and display actually the angle in degrees for some roots. However, you need to remember that we need to give the answers in radians when it comes to the exam. So to find the roots, of course, it's quite easy. 5 zeros, and they can be displayed either in polar or Cartesian form, depending how your calculator is set up. So that's all I had prepared for today. Again, there is the student handout in Google Drive with some more examples, and you will be able to practice some of those concepts we learned today. Thank you for listening.